Welcome back to The Explainer. So today we're cracking open an absolutely massive, unsolved cosmic mystery hiding right above us in the night sky. I mean, for decades now, astronomers have been staring at one of the most stunning structures in our entire galaxy, knowing that something huge, or well, actually thousands of huge things, were just missing. It's a mystery that has completely baffled the scientific community for years, but thanks to some pretty incredible new cosmic detective work, we finally have a breakthrough. Let's look at the evidence.
Okay, let's dive right into this with a really big number, 10,000. See, based on everything we know about how stars live, age, and eventually die, our model strongly suggested astronomers should find roughly 10,000 stellar mass black holes scattered all throughout the Omega Centauri cluster. These are, those incredibly dense remnants left behind by exploding stars. But when astronomers actually went looking for them over the last few decades, zero. Literally nothing. They were just completely missing.
And that leads us directly into what is basically a massive astronomical cold case. Seriously, where have 10,000 black holes been hiding? We're talking about incredibly dense objects with gravity so intense that not even light can escape. So how on earth could a population of 10,000 gravitational behemoths just vanish from view, leaving absolutely zero trace for decades? It didn't make any sense, and it totally challenged our fundamental understanding of these environments.
To really wrap our heads around the scale of this challenge, we have to look at the scene of the crime. Omega Centauri is this massive globular star cluster made up of roughly 10 million gravitationally bound stars. Think about that for a second. Imagine trying to search for dormant, entirely invisible black holes inside a highly crowded, brilliantly illuminated neighborhood of 10 million tightly packed stars. It's the ultimate cosmic needle in a haystack scenario. It's vast, it's insanely crowded, and it's sitting about 18,000 light-years away from Earth.
Which perfectly illustrates why the old search methods just weren't cutting it. Traditional approaches usually relied on things like the radial velocity method, or they looked for radio and X-ray emissions. But here's the catch with that. Those X-ray emissions, they usually only happen when material is actively falling into a black hole. So if a black hole is dormant and isn't actively feeding on a nearby star, you get no X-rays. Those methods totally failed to find this missing population. And that failure forced scientists to pivot to a brand new forensic tool, astrometry.
So what exactly is astrometry? Well, it's the precise measurement of the very small movements of stars over time. Instead of trying to spot the black hole itself, which, again, is invisible, you look for its gravitational influence on the visible stuff around it. Think of it kind of like a painstaking cosmic stakeout. Detectives aren't looking for some flashy X-ray flare. They're just patiently watching a single visible star's minute, seemingly inexplicable movements across the sky, just waiting to see if it's being tugged by an invisible partner lurking in the dark.
And let me tell you, this was not a quick fix or an overnight discovery. Looking at the timeline, this was an epic 20-plus year stakeout. A team of astronomers, led by researchers out of the University of Utah, painstakingly sifted through archival data from NASA's Hubble Space Telescope spanning all the way from 2002 right up to 2023. They were carefully charting the exact path of a star during its closest approach to an unseen companion, right when it moved the fastest. And to finally crack the case, they brought in recent near-infrared data from the James Webb Space Telescope to refine those astrometric measurements to a frankly unbelievable degree.
To really appreciate the scale of what they pulled off here, listen to this quote from the study's lead author, Matthew Whitaker. He said, "The precision of these measurements is incredible, down to a fraction of a pixel on Hubble and Webb's detectors. Just imagine the sheer technical marvel of that for a second. They are charting the exact movement of a star 18,000 light-years away by measuring shifts smaller than a single pixel on a camera detector." Whitaker pointed out that it simply would not have been possible to find this invisible object without both of these incredible space telescopes working in tandem.
Section 2. Meet the suspect, Omega Cat BH-2.
So, Omega Cat BH2 is sitting 18,000 light-years away, and it clocks in at 4.46 solar masses. But the real headline here is its orbit. The visible companion star actually takes 94 years to complete a single orbit around this black hole. That makes it the longest period black hole binary system ever discovered. It's this incredibly slow 94-year dance between a visible main sequence star and an invisible behemoth.
But making that definitive identification required a really rigorous process of elimination to rule out false leads. Actually, scratch that. A previous study by a different group had already looked at this and suggested the binary system might just include a neutron star. But by expanding on the old data with the combined unmatched power of Hubble and Webb, the new team could perfectly constrain the masses. The visible main sequence star was already known to be 0.78 solar masses, but they calculated the invisible companion's mass at 4.46 solar masses, and that is simply way too heavy to be a neutron star, which firmly confirmed they were looking at a stellar mass black hole.
Now, what's really fascinating about the specific dynamics of this duo is the math. You've got this 0.78 solar mass visible star orbiting a 4.46 solar mass black hole. But that 4.46 number, that's actually surprisingly low for a black hole forming in a metal-poor environment like Omega Centauri. As co-author Anil Seth pointed out, we didn't even fully know a metal-poor star could form a black hole quite like this. So this unexpected twist is a huge deal. It gives researchers brand new, hard data to use when modeling how black holes are actually born in these extremely unique environments.
And, as it turns out, this relationship, it's just a temporary alliance. Because of that incredibly long 94-year orbit, the star and the black hole are actually relatively far apart. Researchers calculate that a system like this will probably survive for less than 1 billion years before gravitational encounters with other nearby passing stars just completely tear them apart. Now, compare that to the fact that Omega Centauri is approximately 12 billion years old. This fleeting, temporary connection heavily implies that they didn't form together at the dawn of the cluster. Instead, they dynamically found each other later in life, right amidst the absolute chaos of the cluster.
Section 3. The Ripple Effect. Why this discovery matters.
The big picture impacts of this discovery are absolutely profound. First off, finding this missing population refines our foundational theories on exactly how black holes form in globular clusters. Second, it proves that these dynamic binaries, stars and black holes randomly finding each other much later in life, really do happen. And finally, understanding these dynamically forming binaries is absolutely vital for decoding gravitational wave events. Environments like Omega Centauri are the primary places where we think these binary systems eventually merge, sending out those massive gravitational ripples across the very fabric of space and time.
And honestly, the best part is that this is just the beginning of the story. The future of this hunt is looking incredibly bright. While astronomers are definitely going to keep using Hubble and Webb to search Omega Centauri, they're also eagerly anticipating the launch of NASA's upcoming Nancy Grace Roman Space Telescope. Roman is going to be able to image the crowded galactic bulge with Hubble-like resolution, but with a massively wider field of view. Its regular cadence of observations is exactly what we need to catch the precise fraction of a pixel movements of even more of these hidden binary systems.
So I want to leave you with this final thought. How many more cosmic duos are waiting out there to be found in the dark? We finally tracked down one of Omega Centauri's 10,000 missing black holes, and it took 20 years of patience, fractions of a pixel of precision, and just relentless astronomical detective work. As our tools get better and as space telescopes grow more and more advanced, you really have to wonder, what other invisible behemoths are dancing just out of sight, waiting to be brought into the light? Thank you so much for joining me on this explainer, and keep looking up